Good day everyone. This video brings you to part 1 of chapter 2, and we're trying to explore what is the main equipment available in the IPS. And the outlines for these chapters are introduction, distribution transformer and reactor, instrument transformers, switchgear, power cables, protective devices, and MCC. So the main equipment in the IPS, as we have known from chapter 1, is the distribution transformer. This is the big piece of the equipment available, and it is the most expensive cost for the equipment. And after that, from the transformer, we lay the cable to the switchgear, and from this switchgear, our power will be segregated to the rest of the part of the IPS using the power cables. And of course, during the operation of our plant, we need some compensation, such as the voltage regulator to compensate our power factor corrections. And of course, we need to protect our capitals, right? Our capitals, for example, the transformer, the motors, and the generators, as well as the switchgear. Then we need to use the protective devices, such as the fuses and the circuit breakers. And finally, we'll have a special groups of the so-called the loading center. In the IPS, normally we don't call it as a loading center or load center. Rather, we call it as a motor control center, and this is the group of the motors that being served by a controller or a drives in a specific cabinet. And this is the illustrations of the IPS when we enter a factory. For example, the incoming distributions will be in front of you. So the ratings of this the transformer will be from 132 kV to about 11 kV. And normally when we pack the switchgear after the distribution transformer, what we are going to make the concern is the switchgear kV. The switchgear kV, if you look at here, is 12 kV. And this is purposely done because we need to cater some the voltage surge sometimes from the transformer. So that's why the ratings of the switchgear is always higher a little bit from our incoming. For example, in this case is 11 kV. If our transformer is 11 kV, then we need to choose the switchgear for 12 kV. And from this main switchgear, so we'll go to the switchboard, or sometimes we call it as in other words like a panel board. So this is smaller. This is smaller in terms of the voltage. So that means from the switchgear there is a step down transformer to step down from 11, for example, from 11 kV to 415. And the switchboard selection also, the rating for the switchboard selection also, even though our loading is 415, but our ratings selected for this switchboard must be higher a little bit, say 440 volt as compared to 415. Then for example, this switchboard 1 will serve a series of the MCC, for example MCC 1, MCC 2. And the switchboard 2 is for the general purpose. For example, you have the lightings, DB distribution board, and the general sockets, GB. So this is the overview of the IPS. And nowadays we know that AI is penetrated into our life, the AI, artificial intelligence, and no doubts it also been practiced a lot in the IPS. So as usual, so we lay the cable from the power transformer here, the distribution transformer, and they go to the power distribution, which is our switchgear, and go further to the medium voltage, for example from 11 kV to 6.6 kV or 3.3 kV. It depends on our medium voltage needs. and further it will lead to the much lower voltage, for example 415. Okay, and what's interesting is everything here is controlled by a control rooms. For example, we have various types of the control rooms. For example, the SCADA system, the HMI system. HMI is the human machine interface. That means we can monitor our voltage, monitor our the currents, monitor our power flows to each section or each part of our plants. So that is the intelligence approach. Yeah? That's intelligent approach. Even though we can control our power factor, let's say our power factor is going down suddenly due to the load here, and our control rooms here will detect the power factor, the poor power factor, and it will instruct automatically to increase back the power factor, for example. Same to the voltage. And now we focus on 2.2 is the distribution transformer. Okay, so this is a piece of the a big distribution transformer or a power transformer. So if it is applied at the generation, so we call it as a power transformer. So for example, at the generation stations of the TMB, so we will have the step-up transformer. So that step-up transformer is called as the power transformer. But when it comes to the transmission or distribution, so we try to step down the voltage. So in that case, the transformer is called as a distribution transformer. So as you can see here, this is one types of the transformer. So the main parts of this transformer is normally, as we have learned previously, so it has the core and magnetic circuits, so which is the core, and the winding as well. So it has the winding, and in some types, specific types of the transformer, they have the tank, so called the tank conservator tanks. This is where the oil immersed type of the transformer having the conservator tanks. And what is the function of this tank is actually to control the level of the oil as the installations material in the winding here. And this one I don't want to talk much on that because this is a very basics. We have basically core types of the transformer and the shell type of the transformer. So this is this shown you to the core types of the transformer, which is typically used in the distribution transformer. Okay? And the shell type transformer normally is used for the generator. It's used at the generation site or the step-up transformer. As I told you just now, that is the power transformer. So next we look at the tap changes. So why we need the tap changes? Because our transformer is serving the the loads, and most of the functions for the transformer is the main function of the transformer is to step up or step down the voltage. So that's why we need to use the tap changes to adjust the voltage levels when it is needed. And basically this tap changes is divided into two types. So the first one is the off circuit taps. So that means you need to de-energize this transformer before you can adjust the tapping. So this is the off circuit tap. So the second type of the tap changer is the load tap changes. So this one is the taps is automatically done while the loading is still operating. So the loading is still carrying on. I mean, you don't need to de-energize this transformer. You don't need to switch off this transformer just to adjust the tap. Okay. and usually it is placed at the primary windings. Why? Because at the primary windings for the distribution transformer, the voltage is higher. The voltage is higher as compared to the secondary. So when the voltage is higher at the primary, so the current will be much more lower. Okay, that's why we are placing the tap changer at the primary winding, just to minimize the spike, the spike. So when it's switch, let's say from step 1 to step 2, for example, they have the spike, and that means when your current is higher, that means the spike is also higher. So that's why we need to avoid these unwanted phenomenon, right? So the most important is we need to reduce the spikes due to the or the surge currents due to these switchings operation. And for the off-circuit taps, is normally used in the industrial power system, okay, with 4 full capacity taps. 4 full capacity taps, that means you have 5 positions from, let's say, the normal one, 0, 1, 2, 3, and 4. So each tap will provide about 2.5% per step. So why 2.5? Because our allowable tolerance for the voltage is 10%, plus minus 10%. So that's why one step is equivalent to 2.5. So that means at the let's say at the upper scale, so that means positive 10%. So that means once you adjust from 0 to 1 step, so you has increased the voltage 2.5%. Okay, so that is the meaning. And for the load tap changes, so it is normally used for oil immersed types of the transformer, and usually this type of the transformer, the voltage is higher, is much higher. It is more than 34.5 kV. Even though you having the 33 kV also, it is the off circuit types. It should be more than 34.5 kV. Then we so-called economically use the load tap changes. Otherwise it's not that economic, because the load tap changes is much more expensive as compared to the off circuits type. And here you have one example. The types of voltage is, as I told you just now, is the variation is plus minus 10%. So that's why the tap changes is provided to adjust the voltage regulation of plus minus 10% in either 16 or 32 steps. So this is for the load tap changes. Previously was the off circuit tap changes. So this is the load tap changes. So that's why the step is more than the off type changes. So it's normally it consists of 16 or 32 steps. So you can adjust, let's say you can calculate. So in 16 steps of the load tap changes, so one step is equivalent to how many percent? Okay, so don't forget it is plus minus. That means you have plus 10 and minus 10. So altogether is 20%. Okay, plus 10% and minus 10% at the bottom side. So in the total you have 20%. So 20%. So if you divide by 16, so that means you have one step is equivalent to 1.25%. Okay, and same to the, if you have 32 steps, so you just divide 20% divide by 32 steps, so you will have 0.625%. So that is the I mean the step is more precise. It's more precise as compared to the off tap changes. So the type of the distribution transformer, normally we have oil field, or we call it as oil immersed types of the transformer, And the second one is quite rare to use, non-flammable liquid fuel. And finally, this is the dry types transformer. And the dry type transformer is the most famous in the IPS, especially for the indoor application. So this is the oil immersed types of the distribution transformer. So the important parts of this distribution transformer are the oil conservative, the conservator tank, and another one is the bushel relay. The bushel relay is to protect this piece of the distribution transformer during the overloaded or short circuit conditions. During the short circuit condition, and basically in the bushel relay there is two sides. There's two sides. If overload, then it will switch to the overload protection, and if short circuit, let's say ground, let's say a single phase to ground faults happen, and it will shift to the short circuits operations. So that is the so-called the bushel relay. Bushel relay is for the protections, to protect the distribution transformer. And other is just a tap changes, and you have the tap changes, and then you have low voltage bushing and the high voltage bushing. This is a connector, connect to the high voltage side, and this is connected to the low voltage sides. Of course, we have the thermometer to measure or to monitor the temperature rise in the oil, or indirectly for the winding. Okay, and we have the rest is just not that important, because it is a general parts, like a rating plate, and the name plate here, the roller, just to handle the handling purposes. And you have the lifting lug also for handling or transportation purpose. You just use this lifting lug. And another one is the air dehumidifier. Air dehumidifier is to rid off the moisture contents. Moisture contents during the operations of the oil here. So the oils, normally it will have the moisture content, and we try to rid off using the dehumidifier. And this oil immersed types of the transformer is normally up to 2.5 MVA to be used in the IPS. So normally our IPS is not that big as compared to the transmission or the distributions sections for the our supplier. And normally it consists of two types. So the first type is the permanently sealed tank. Implied by the name, it is permanent sealed tank. I mean, we no need to maintain it, so that it is a maintenance free, but it's more expensive. This type of the permanent sealed tanks, normally we call it as a hermetically sealed. Hermetically sealed, to prevent what? To prevent the oxygen, nitrogen, and the moisture content with contact with our oil. Because once these elements contacted to our oil, then our oil will be degraded. So that's why it is kind of the permanent seal tank. Another one is the tank with the conservator, like we saw previously. We have one conservator tank. So this tank we normally needs to do the maintenance, the monitoring, just to make sure the oil quality is still good, is still in the good conditions. Otherwise, it will give a very big impact to the transformer. Even though the worst case is the explosion. So normally, what is the type of the oil used for the tank? And this is the most commonly used, the mineral oil or the synthetic oil. And silicone oil also is one of the normally used. These oil are the non so-called the a non environmentally friendly oil, okay? Because so it will give harm to the our environment. And recently they use the so-called the ester oil. Ester oil is the environmentally friendly oil, and it extracts normally from the let's say for example the soybeans oil. Okay? So recently in Malaysia they are trying to replace the transformer oil using the palm oil. The palm oil. So it is very eco-friendly or alternative oil for the transformer. And you can compare the property between the mineral oil and the ester oils, as here. So this is the mineral oil, and this is natural ester. This is synthetic ester. It's synthetic ester. So that means it is not 100% natural. That means it's the combination between the mineral and the natural ester. So this is so-called the synthetic ester. And we look at the performance, the comparison of the property. So we compare the fire point. Okay. So what is the fire point? I mean, if it exceeds 180 degrees Celsius, that means it will be get fired so easily after the fire point here. So I mean the higher the fire point, the better is the oil. So the natural ester is 360, so it's double of the mineral oil. So it's much more preferable oil. So the flash point, so the flash point also, the higher is the better. Okay, the flash point. Otherwise it will have the flash over. Okay, so this is 330 degrees Celsius, and this is just 160 degrees Celsius. Biodegradable, yes, this is of course the natural ester is a biodegradable. And what about the toxic? The toxic, this is non-toxic, this is the toxic. Okay, this toxic. That's why it is not environmentally friendly. And viscosity, this one is a little bit sticky, a little bit sticky as compared to this one. So this is much more thicker, in terms of the liquids, so it is much more thicker. And what about the thermal aging? This is much better. This is much better, but this is the best because the viscosity is in between this one and this one. Okay. And how we maintain, and what is the things that we need to take care during the maintenance of this oil immersed type of the distribution transformer. Is the first one is the dielectric strength. So we try to monitor always the dielectric strength, as well as the second one is the acidity, the acid. So this is the feature. If the dielectric strength, this is the criteria. Dielectric strength is less than 50 kilovolts. That means if you give the high voltage, so it only stand for less than 50 kilovolts per minute. So that means after this after we apply more than 50 kV, so it will have the flash over. That means the dielectric strength is not that good. It's not that good. So it must be less than 50 kV. If 50 kV for 1 minute. So if less than 1 minute, that means if when you test it, so if have the a flash over within 1 minute, that means let's say in 20 seconds or 30 seconds, so that means we need to change the oil. Okay. So another one is acidity. So if acidity is above 0.4 milligrams of the potassium hydroxide, or KOH per gram, so this is the indicator. that means the oil should be replaced or filtered. You can see the change in the color, right? So this is the best one, and this is the poor quality one with I think is the acidic, is acidic oil. This is how we test for the first one, dielectric strength. So that means we uh, inject the high voltage, and let's say 50 kV here, so it must stand for 1 minute. If there is a flash over between this conductor and this conductor in within 1 minute, so that means we need to replace it. And now we focus on the cooling methods, the cooling method. So how we read when we purchase a distribution transformer. So it has 4 letters. It has 4 letters to indicate the cooling methods. So this is the 4 letters. The first one is the O, K, or L. So what is the O, K, or L? So it depends on the flash point. It depends on the flash point. And this is the internal cooling medium, and this is for the internal cooling medium. This is internal cooling medium. So what type of the medium it use? Internal, inside the transformer. And the second letter is the NFD, or either N, F, or D. So this is for the mechanism. So what types of the mechanism it used for circulate the cooling mediums. So this is the mechanism, still internal. So these two belongs to internal. These two, the rest 3 and 4 belongs to the external. The external. Okay, so this is the external cooling medium. So you have A and W. A and W. A is the air and W is the water. So air, that means is use the natural air to cooling down as a medium. And number 4 is the circulation mechanism. Circulation mechanism for external. So these two are external, and 1 and 2 are the internals. Okay, so this is the circulation mechanism to cooling down the mediums, as stated in 3. So what is the meaning of these letter O, K, L, N, F, D, A, W, and NF? So we will explore it now. So for the internal, the first letter, second letter, third letter, and the fourth letter, right? So for the first letter, as I told you, O, K, and L is depends on the flash point. So the flash point, as we have seen just now, the flash points for the mineral oil, natural oil, so it's 160 and 330. Okay, so this is the flash point. So for the O, that means when you purchase the transformer, when you see the letter, the first letter is O, that means the flash point is less or equal to the 300 degrees Celsius. 300 degrees Celsius. So you can imagine the 300 degrees Celsius is only this one, the mineral water, the mineral oil is only used for the mineral oil. So it's impossible using the natural ester, because natural ester is 330. Okay, 330, and this one is only 160. It could be synthetic ester as well, 260. Okay. And the K and L is also the definition is greater than 300. So this is possible for the natural ester. Okay. And L is there is no measurable flash point. Okay, there is no specific flash point indications. And for the second letter is, if you see N, it is the natural. N is natural, natural convictions, natural conviction. So that means it's just circulates naturally. And F is the by force. By force, how we going to force the circulations? So normally we're using the fan, and using the fans, and by force circulation through a cooling equipment, natural convection in windings. And D is the force directly, directed, is force directed to a specific area, specific parts of the winding, right? And for the external, the third letter is A, W. A is air, W is water. So external, we have air or water only. So of course, when you use water, you need to use the pump. Use the pump. That means that is the forced circulations. Okay? If you use air, so normally we will use the natural convections and natural convection, or it could be F also, force using the fan. Using the fan. Okay, so for example here, so if you have the transformer here, so this is a transformer, so this is the internal cooling system. So internal here we use what, internal we use O is the oil, okay? N is the natural, so that means the convection is by nature, naturally flow inside the transformer. So O N A F, so this is the external, so this is the external cooling, and the medium is A, which is using air and the natural air. And what is the mechanism is using the fan. So this is your fan, you see, so this is the fan, cooling fan. Okay. So this is how we read the cooling methods for the distribution transformer. Same to this one, you can read O-N. O-N is for the internal, O is the oil, so they use the oil, and N is the natural, and outside it use the air, also air, but this time it is using the N, natural, so it's still air but without the fan. There is no fan, it just circulate naturally, right? And some of the transformer, they have more than one cooling system. For example, this one is one only, so this one is only one, this one also only one, but this one, if you look at this one, it has a O-N, O-N-F, and O-N-F, so that means 2 times O-N-F. That means it has 2 stages of the fan cooling. Okay, so for example here you have O-N, O-D-F, O-D-F, and O-D-F. So you have 2 stages of the directed, because D is the directed, directed fan cooling. So this is how we reach the cooling methods for the distribution transformer. So the dry types of the transformer, basically we have 3 types of the dry transformer. So the first one is the vacuum pressure impregnation, and the impregnations in the polyester or the silicone varnish. This is the vacuum pressure, and this is much cheaper because it's less expensive. Need clean environments. You cannot place it at the dirty environment, for example in the store, for example in a very dusty environment in your factory, cannot. So you have to choose these 2, either one. So this one is can be parked only at the clean environment, and it's mechanically weak against the faults. It's mechanically weak due to the insulations here. It's only use the vacuum pressure. And the second one and the third one is the cast oil or the cast resin, because this is the mechanically short circuit proof. So it is mechanically strong against the short circuits, because the insulations here is using the cast oil or the cast coil or cast resin. Another one is the VPI epoxy. So this is the mechanically strong also against the fault currents. It's always, because the winding is always sealed with the epoxy. Of course it is not cheap as compared to this one, so it's very expensive. Okay, so this is the dry types installations and the insulation. So this is the insulation class. So you have 180, 185, and 220. So the class is F, H, and more than H. Okay, so what is the meaning is when you have the F, for example, so the ambient temperature is about 30. Okay? In average, you have 30, the ambient temperature where the transformer is operating, and the maximum ambient temperature is 40 only. Okay, the 40. And this is the average winding temperature rise. Okay, average temperature rise at the winding. So it has 115 for F class, 115 for H class also, and this is for more than H is 150. Okay, so this is the winding hottest temperature rise. So this is the hottest, this is the average, and this is the hottest. So that's why it is higher than this one, 140, 145, and 180. So this is the permitted winding temperature. So this is the final temperature. So how to obtain this one is actually this one, the hottest temperature plus the maximum ambient temperature. Then you get 180 here. So for example, 185 is 145 plus 40 here. So it's 220 is 180 plus 40. So that this is depend on the hottest and the maximum ambient temperature. So that's why the recommended temperature is normally at the average, so 80 only. Okay, so the recommended temperature rise is only 80. And this is the rating, the typical ratings when you are going to choose for your distribution transformer. So this one is very useful, especially for your project as well. So you need to refer to these tables. The first column is the primary. What is the primary KV? And the second column is the secondary KV. So what is the secondary KV? For example, you are looking for let's say from 11 kV to let's say 6.6 kV. Then you can choose which one. 11 kV. So 11 kV is either this one or this one, and 6.6 kV. This one has no 6.6 kV, but this one having 6.6 kV. So maybe you can choose this one. And another thing you need to consider is the rating. That means the kVA. So this is the capacity or the size of the transformer. This is only available size for these kV ratings. And the construction type is the oil types. So this is the impedance, the percentage of ZEC, the impedance range. The lower the more expensive is it. It is. That means the lower the impedance range, the more expensive of the transformer. Why? Because when you have a lower impedance, that means your short circuit capacity is higher. It's higher. So that means it is a good thing when you have the higher short circuit capacity. Okay? And how to choose between the dry and oil types. So it's depend on four characteristics or the four specifications. Number one, we need to consider the availability of the ratings. Okay, the availability of the ratings. Of course, the dry type transformer is only available in a certain rating only, as we can see here. So this is dry types, and this is dry type, and the rest is just the oil types. So that means it's very limited in terms of the availability. The availability. So the second consideration is the cost, and the lower is the location you need to put your transformer. The cost. So of course the cost, in terms of cost, oil field is much cheaper. It's much cheaper compared to the dry types. The dry types. So the oil field is 20 to 30% cheaper, because in the dry types, this one is meaning when you choose the same ratings of the transformer, right? So let's say 1 MVA transformer. Okay, you compare the dry and the oil type. So of course the oil type is cheaper, because dry type is they have a special insulation and special windings, which is the that means seal with the epoxy, for example, so it is much expensive. So the oil fill is also suitable for outdoor and indoor application. So but the dry types is only for indoor application only. Okay, let's say you wanted to park indoor, that means under the roof, right? Under the roof or inside your plants, that means you can consider for the dry types. Okay, and if you are going to put it outside, that means the only choice is the oil type. Another consideration is the fire building electricity regulations, because we need to buy insurance. We need to buy insurance to protect. And let's say if something unwanted accidents, let's say for example explosion. So this is we tied to the regulation, the fire building and electricity regulation. So of course the oil field is restricted to the regulations, and because the oil, if you are not maintain it wisely or perfectly, that means it might cause the accident and the explosion. So that's why the oil field is much more dangerous. That's why it is very restricted to these regulations. And some locations like the basement and the top floor, the top floor is permitted, okay, to dry type only. So that's why the dry type is normally for the indoor applications. So that's why if you are using the oil types, so the insurance is much more higher. You need to buy more expensive so-called the policy for your insurance. And the last one is for the maintenance. So of course, no doubts, the oil type is need a lot more maintenance works as compared to the dry types. Okay, now we explore the reactor. So what is the reactor? Reactor actually is the inductor, right? Is the inductor. So inductor. So you can found this one either in the distribution station and distribution substations. You can easily find these things, and these are the reactor. Okay, the reactor. So it's very similar to the transformer, but if you look at the transformer constructions, it has two windings. Two windings. One is the primary, and another one is the secondary windings. Okay, either is step up or step down. But in the reactor, it only has one winding per phase. It only have one winding per phase, like this one. And what is the purpose of this reactor? Actually, it can use to control the reactive power and the Q and the reactive power. So it can supply the inductive power. This is more to the voltage regulations. The voltage, when you are going to control the voltage level, so that means you need to give, let's say you need to supply the Q, and at the same time you absorb the capacitive power. Or sometimes we also use this one as the short circuits current limiter, short circuit current limiter. So that when we connect the reactor in series, so it becomes the short circuit current limiter. So it has two construction types. So the first one is the air core, just using air, is nothing here. So it's the air core, air insulated types. And the second one is the liquid insulated. Like for example, inside here you have the oil, the oil guiding washer. So there's only two types, and the applications, as I told you just now, if it is connected in shunt, for example here in shunt reactor, so it's can be act for the compensation work, act as a compensation work, either for switching surge limitations. You can limit the surge, the switching surge. So for example, if you have the power factor corrector, so it always switching to from one and to each other, and during the switching, and there is a spike or surge. So these times we can install the shunt reactor in parallel like this one to absorb or to minimize the surge. And the second one is the reactive compensations. Reactive compensation either to control the voltage or harmonics as a filter. So this is a filter. So if you are connected your reactor in series, it is for the fault current limitation. So you can limit the fault currents. Okay. So how we limit the current? Later we see one example on that. And the rating of the series reactors is normally can be determined by Q. This QR, R is the reactor, QR is equal to square root 3 times the Vx. So what is the Vx? Vx is not the rating, but is the rated voltage drops. Rated voltage drop of the reactor phase to phase in volt. Okay. Which is the voltage drop. It's not the voltage rating of the reactor. And I is the rated current of this is the rated current of the reactor. Okay. And the XL is the inductance, and the inductance you can calculate using the voltage drop divided by 3 times the I per phase. It's the ohm per phase. So example here, so we consider a 3-phase reactor. Okay, we have the VR. VR is 33 kV. So VR is the ratings for the reactor. VR is the rating for the reactor is 33 kV, and the voltage drops phase to phase is 3% of the system voltage. Phase to phase, 3%. So this is the Vx. Vx. So the system current for this reactor is 650 ampere. That means we can calculate the size of the reactor. We can calculate the size of the reactor in terms of the kVAR. The kVAR, because it is a Q. kVAR. And how to calculate it? So we begin with the Vx. So Vx is stated here is 3%. So it's 3%, so 3 divided by 100 times 33 kV, so it is about 0.99 or 1 kV. Okay, we can say it is 1 kV, and then we use this 1 kV to obtain the XL. And the XL is 1 kV divided by 3 times 650, so you obtain 0.89 ohm per phase. 0.89 ohm per phase. So that is the X, the reactance. And the size of the 3-phase reactor. So this is a 3-phase. If we calculate for the 3-phase reactor, Q is equal to 3 times 1 kV, because this the Vx is 1 kV, and times 650. 650 ampere. So that means this is our size of the 3-phase reactor when we apply to 650 ampere of the currents. So it's 1125 kVAR. So for the single phase, is 1 kV times V times I divided by 3. It is 375 kVAR. Or we can say that single phase, so the 3-phase is equal to the 3 times single phase. 3 times the single phase size is the 3-phase size. That means 3-phase size, this one 1125 is equal to 3 times 375 of the single phase. So the second example is consider a distribution system like this one. You have a grid connected here, and with a transformer, a step-down transformer, 33 to 11 kV. So with the percentage Z is 7.15%, and another one is running in parallels. The tandem is in parallels in a generator. So this one is operate to each other. Generator is 2.5 MVA, 11 kV, and the percentage Z is 25%. 25%. So let's say you have fault here, and this is 3-phase, and we try to limit the fault current here. We try to limit the fault current. Okay, so we look at the original ratings. So the transformer is 5 MVA, so the generator is 2.5. Okay, and the reactance, the most important now is the reactance. When you're dealing with the short circuits calculation, the most important is the reactance, that means the percentage X here. So this is 7.15, this is 25. Okay, and a three-phase faults, the three-phase faults, so you can calculate it like this one. The fault MVA is equal to the base MVA, so we need to choose a base MVA later on, divide by Z's equivalence. Okay, so the Z equivalence, so the base for the MVA we takes as 5 MVA, or 5000 kVA, 11 kV. So this is our base, and thus the generator reactance at new base, and the generator here previously was 25. So due to the base selection here, so we need to calculate the new base, the new base for the reactant at the generator. So it's 25 times this is the new MVA base divided by the old one, and the old one is 2500 kVA, which is now the new reactance for the generator is 50%. Okay, 50%. So like this one, so it's 50% and 7.15 here. And due to the fault here, we try to reduce the fault current later on. So how to reduce it? That means we need to have the series reactance here. Okay? We need to install a series reactance here. So how much is the series reactance? Now we calculate for that. Okay, the equivalent impedance, the Z percentage of the combined power system. Okay, the impedance. So it's 1 over, because it is in parallel, so that means you can use your parallel circuits calculation. 1 over Z equivalent is equal to 1 over, this is for the so-called transformer, and this is the generator. Okay. And then the Z equivalence now is 0.0625 per unit. Okay, and thus once you have the Z equivalent here, you can calculate the fault levels. Okay, the fault level. So the fault level is 5000. This is the short circuit capacity, the short circuit capacity, or we call it as a fault level. Fault level is 5000 kVA divided by the Z, 0.0625. It is about 80 MVA. It is 80 MVA. So now we try to limit the fault level to 50 only. Okay, instead of 80. So now we try to limit it to 50 MVA only. So by installing a series reactance like previously, like this one. So we install a new installation for the series reactance, just to limit from 80 to reduce from 80 to 50 MVA only. Okay, now we need to calculate back the new equivalent impedance. Okay, so since we have 50 MVA, we only limit 50 MVA. Now we change this 80 MVA with 50 MVA. Okay, and this is 5 MVA is this one. Okay, then our targeted Z equivalence is 0.1, okay, rather than 0.0625 just now. So now our targeted Z equivalent is 0.1. So that's why 1 over 0.1 here, okay, is equal to 1 over, this is the transformer, plus, because it is in series, this is in series reactant, plus X here, and this is for the generator, and we can obtain the X. X is 0.0535 or 5.35% at 5 MVA and 11 kV base. Okay, so that's why the series reactance selection is 5.35%. Okay. So the instrument transformer is not much because normally this is just a small device, instrument transformer. The application is for meterings. It's used for meterings, for billing, for example, and protection control. That means we need to step down the voltage or step down the currents for the protections to give to the relay, for example. And another purpose of the instrument transformer is in the load survey. In the load survey, So load survey, this one is normally we need to understand the conditions of our plants, then we have to use the instrument transformer to step down the voltage or current. And this is a symbol. This is a symbol for the current transformer. So you can see the dot here. The dots here actually is the where the current is entered. Like for example here, so the current is entered from this side. So if the dot is shifted to here, that means the current is entered through these sides. Okay, so in this case, it is entered through this side and going out for another dot. Okay. Same to the voltage. So if the voltage is this is the positive side. Okay, so this is the positive side. Okay, so this is illustrations of the current transformer and the voltage transformer. Okay. So if you look at here, you have the current transformer. So you have the voltage transformer here, and of course the rest is just a wattmeter. You have the current voltage relay, okay, and current relay. So this is for the protections, and this is to monitor, just to monitor. This is for the protections, okay, monitor. Or for the load survey also we use the wattmeter here. Okay, so let's say this is your transformer, and then you're trying to analyze what is the voltage and the current as well as the power at the primary sides here. Then you can use the instrument transformer. Okay, so you can read through these descriptions about at section A, what is that? At section B, what is that? The section B is to show you the polarity markers. That mean the dots here, and the dot here, that means you have dot here, that means the current is entering this side, through this side. It's not that this side. Okay, and then it's going out through another dot here, the marker. So that is the meaning. We call it as an instantaneous direction, of the current. So the potential transformer at the switchyard, so this is the illustrations. Normally it's like this one, is if you open this box, and this is the current transformer applications. Current transformer application inside the switchgear. This is where I snaps from the factory, the manufacturer of the switchgear last time in Penang. Okay, the switchgear, as I told you, the rating must be slightly higher than the incoming. Let's say the incoming is 11 kV. Now you choose for 12 kV. Okay, so the function of the switchgear is the PIC. The PIC is the protections, isolation, and control. So it's a protection, no doubt. You have a lot of the switches, or you have a lot of the disconnector or the circuit breaker here. Okay, circuit breaker, including the vacuum circuit breaker types. Okay, so that is a protection. For isolations, of course, you have the switching. And the switching to isolate. Let's say you wanted to have the maintenance at certain part, and then you switch off or you disconnect that parts from the rest of the plants. So that one is the isolation. And another function of the switchgear is to control. That means you must know what is the voltage level, what is the current level through the metering here. Okay, so these protections. The protection normally is protects against the overloads, the short circuit, the insulation failure, or under voltage. So this is under voltage is much crucial in the IPS as compared to the over voltage, because our loads is always overloads. It's always might have the overloads conditions in the IPS rather than a light load or underload. And the isolation is isolate faulty sections. For example, you have a fault happen at one section. That means you need to clear that fault. Then you have to isolate that particular section. So the isolation energize sections for maintenance. For example, you have a smaller step step down transformer there, so you need to do maintenance on that transformer. Then you have to de-energize the transformer, and you have to isolate it from the switchgear connections. Okay, for the control, so of course it's the functional switching, so it's more to the switching and the metering. So let's say you have the emergency stop, okay, then it will control through the switchgear, okay, and the measurement as well using the metering. So we can see what is the main component inside the switchgear. So because normally what we can see is just a cabinet, the metal cabinet like this one. We do not know what is inside here. So inside here you can see the first one, of course, it is connected to the transformer, our distribution transformer, the incoming feeder. We call it as an incoming feeder. So the incoming feeder is connected to the distribution transformer, and after that, when you need to segregate or distribute your power to the rest of the factory's sections, you have to use the bus bar. Okay, use the bus bar. This one is the common point, and of course to protect it, you need the circuit breaker, the contactors, okay, and the fuses. The fuse is a very big like this one. It's not a small electronics fuse as what you can see in the laboratory. So this is a very huge one. And the isolator is isolator or disconnector. Just connect, isolate during the faulty condition or maintenance. This is the front panels I took from the factory last time. And basically the magnitudes in the switchgear, normally we consider the voltage, current, and the frequency, as well as short circuit power. Okay, so for the voltage, so the voltage, let's say this is the rated voltage. This is the rated voltage, let's say 7.2, and then the maximum it can go is up to 60 here. It's up to 60. So let's say you choose 12 kV. So 12 kV. So the maximum it can go is the upper. U is the European standard symbol for voltage. U. The European normally they use U, the symbol of the voltage. UP. P is the peak. UP. This is a UD. D is the down. Down is the minimum. Okay? So this is the rated during the lightning strike. The lightning strike. Okay. So that means the lightning strikes, what is the maximum it can go is depend on this one, okay, due to the lightning strike here. So the currents is the rated currents, operating currents, and short circuit withstand currents. It's normally 1 second or 3 seconds. The peak withstand current also, and the peak withstand current here, this one. Okay, so normally is 1 second or 3 seconds. But in the lightning is about the microsecond. It's in the microseconds. Okay. So this is about the faults and the fault currents, and the frequency, of course, is depends on the plus minus 1%. Okay. And the short circuit power also is depend much on the fault current. So now we go for the power cables. Section 2.5. So normally what we can see in the factory, so there is two types of the cables they use. One is so-called the power cables, and the power cable implied by the name is used for handling the power. For example, you have laid the cables from the feeder to the MCC, for example. So that the cable is the power cables. So another cables type is the control cable. This is used for the metering. For example, you have the instrument transformer. Okay, that means used for the metering purposes, metering or protection purposes. Of course, the size is much smaller as compared to the power cable here. As well as the ampacity. Ampacity is the what is the maximum carrying current, and the carrying currents of these cables. So this is called as a ampacity, and the maximum carrying current. So this is the illustration for the power cables. So of course, outside here you have the jackets, and the jacket overall cable jackets. And then you have the concentric neutral, and this is the neutral, and further you have the insulation shield. This is the insulation shield. So this one is the neutral point, the neutral. Okay, and insulation, after the insulation you have another insulation. This is the so-called this is the shield, shield for EMC purpose, for the EMC purpose, and because we don't want our cables when they carry the current, so it will disturb the rest of the equipment of the devices in terms of the EMC, electromagnetics interference, EMI or in EMC compatibility. So that's why we need to use the shielding. Okay, then this is the insulation. Insulation, you have various types. You have the basic one is the paper type. We use the paper as the insulator. This is the EPR, and sometimes we use the XLPE, for example, so that it's a high grades of the insulation as compared to the paper. This one is extruded conductor shield. So we have double shield. Okay, so this is shield directly to the contacts of the conductor, and this one is after a piece of the insulations, another shield. Okay. And finally we have the conductor, either is aluminum or a copper, right? Okay, type of the conductor. Now we're talking about the conductor itself, the conductor in the cables. So the first, you have the solid conductor. What is so-called the solid conductor? Solid conductor is only has one only, like this one is one piece of the conductor. So this is so-called the solid conductor. Another one is a stranded conductor. Stranded conductor, you have many smaller solid conductor. That means it's it's stranded together. This is the work here is so-called the strain. Is straining. Is straining together. Is twist together or stranded conductor. So this is normally used the concentric stranding. Normally, it's like this one. Okay. So this is so-called the concentric straining. Concentric. It's just concentrate like that. It is not like this one. It's a smaller wire. So normally in the electronic, so we have a smaller wire stranded conductor like this one, but in power cables normally we use the concentric straining like this one. So it is more organized like this one. Okay, so this is the you can see this is the conductor. Okay, so this is the neutral. The neutral. This is the insulation, the insulation here. So of course you have the shield here and the shield here, and finally you have the jackets, jacket outside here. Okay, the power cables also classified with respects to the installations. And the first one is the laminated. And laminated, as I told you, they use the paper only. This is the cheapest one. The cheapest one. Another one is the extruded. And the extruded, this one is the extruded, so-called the insulation. Because they use the process extrusions process to wrap the insulator. So the insulator is have a series of the insulator from the rubber compounds, for example the polyethylene, the PE. You see the PE is a polyethylene, or XLPE is a cross-link polyethylene, or the ethylene propylene rubber, EPR. Just now we have a EPR. But anyhow, this is through the extrusion process to the insulation system. And why the insulation is very important? Because the insulation is the only protections to the cable. So once the cable is overloaded, that means the current is higher than the rated current. That means something will happen. So that means the first is the cable will be heat up. Heat up until a certain level, then it will explode. It will explode. So what is the level on that? So the 100% of the levels, we have 133% of the level, we have 173% of level. So what is the level? So this is the withstand levels. So how much is the insulator can withstand? That means, of course, the higher, the more expensive it is. For example, 100%. 100% is normally used to clear the ground fault within 1 minute only. So it only can stand for 1 minute. So that means our relay must be operate within 1 minute to clear the fault. Otherwise, if more than 1 minute, it might cause the explosion to the cables. So that is the meaning with the 100% level. So that means when you purchase the power cables, so the first thing if you need to consider is the insulation, especially these levels. So how much of the level? 100%, 133%. So if 130% you buy for these power levels, power cables, that means it can withstand the ground fault within 1 hour. So that means it is much more, about 60 times of this, the first one. And if you choose this one, the most expensive one, 173 levels, so this is indefinite. So of course it's very, very expensive, this one. So it is recommended for ungrounded system. It's normally for ungrounded system. Ungrounded system, then we have to choose the higher level. Okay, then how to do the selection? I mean the cable sizing and the cable sizing. Then the cable sizings, like the transformer sizing, so we need to have some criteria. So in this case, we have three criteria to analyze the cable sizing. The first one is the short circuit current, and the short circuit current withstand capacity. And the short circuit current withstand capacity. The second one is the continuous current capacity. So how much is the continuous current capacity? That means carrying currents, or we call it as an ampacity here. Finally, we need to analyze the starting and the running voltage drops in that cables. So it also has the voltage drops considerations in the cable sizing. Okay, so otherwise, if you are not properly consider these three, then you might have this one, and this is after burnt cables, this one. And then we laid the cable nicely using the tray like this one. So this is on air, is on air installation, laid on the tray. This is so called the tray of the cables. Okay, we laid like this one. Okay, we look at the first criteria. The first criteria, the short circuit current withstand capacity. So this is to determine the minimum. So the minimum cross-section area. So when you pass the first criteria, it is still not final. It's still not final. You have to go through the second criteria and the third criteria as well, the ampacity and the voltage drop. So this is the first criteria, is to find what is the minimum cross. That means the smallest smallest possible size of the cables, the minimum cross section area of the cables. Okay, so if you fail to check this one, that means your cable might have the overheated. It might have overheated. That's why it will cause the permanent damage, or sometimes explosion, or we call it as a mechanical stress. So that is the mechanical stress of that. And this short circuit current withstand capacity depends much on the magnitude and the duration of the short circuit currents. Okay, we have the short circuit current, and how much is the magnitudes of that short circuit current, and what is the durations. 1 minute, 2 minutes, 5 minutes, and 1 hour of the duration. The longer the duration, the more mechanical stress is the power cable will experience. So the quantity I square T, this is the energy. I square T is the energy. Energy is depend on the time. It's depending on the time. So that's why the longer time of the short circuit current happen, so the more energy it will produce. It will produce. Okay. So that's why this energy will heat up the cables. That's why it is unwanted. And what is the formula? So normally this A is the cross-sectional area, or the size of the cables. It is the square root of the energy square root of the energy. So this is the SC is the short circuit. This is the magnitude of the short circuit current, and this is the period of the short circuit current. So it's a square T divided by K. Okay, this is K. K is what the short circuit temperature rise constant. Okay, we need to find out this one. It depends much on the insulation type. Okay, what type of the insulation they use, and it will give effects to the calculation of the K later on. Okay, K is depends on according to the IEC standard 60364-5-54. So it has two type of the conductor, the copper conductor and the aluminum conductor. So for the copper and conductor, then we have to use this formula to calculate the K. If aluminum, then this is the formula. So if you see 226, that means this is for copper. If you see 148, this is for aluminum conductor calculation for the K. So this is the temperature rise constant, the K. So the T2 minus T1, T2 is the final temperature, T1 is the original, starting temperature. So what is the original temperature? Then this one is after the temperature is raised. Temperature raised up to certain level, then we measure the temperature. So this is the final temperature, and this is the starting temperature. Okay. So for example, so you have a starting initial temperature and the final temperature. We call the final temperature T2, and the initial temperature or starting temperature is the T1. Okay. So this is the type of the insulation, the material of the insulation. If we use the PVC, so the final temperature is 160, and so this is from the manufacturer. So they will provide you this insulation materials specification. So if you use the butyl rubber, so it's 220, so it's much higher than the 160. So normally what we use for the power cable for the higher power application is the XLPE or EPR. Okay. So you can use this T2 and T1 to calculate the K. Okay. For example, here the common value for the K here, for the PVC, for PVC. So you can calculate using this one. You can using this one, for example, and you put in the PVC 160 for T2, 70 for T1, then you can obtain 115 here. 115. This is for copper, this is for aluminum. And the insulation also depends on 1 second or 3 seconds, as we have mentioned just now previously. 1 second protection or 3 second protection. Okay, so normally we calculate for 1 second. 1 second in ampere per meter square. Okay, so this is for 1 second's value, and this is for 3 second value. So how to obtain this 3 second value is very easy. So you just get this value 115 divide by SUT3. Because it's 3 seconds, it is SUT3. Because here we have the SUT-T. Okay, so now you change the T to 3, so it's a SUT3. Okay, so that's why when you have this one 115 divided by SUT3, 3 because of the 3 seconds. It is not about the SUT3 of the power from the single phase to 3 phase. So that is not the SUT3. This SUT3 is for the 3 seconds here. So just simply divide the upper value with SUT3, then you get the lower value here for 3 second current rating. Okay, so the value you can use the equation 1 to determine, and T is to determine next. Okay, so we need to find the T. So the previous one is the standard for the protection, 1 second or 3 seconds. So the actual T, so how much is the T, is much depends on our protective device. For example, fuse, for example, use the so-called the circuit breaker, so it's on when it is switched off. So that is the T. The T we need to be to calculate it properly. So the T, the short circuit current is varying with times. Of course, the short circuit current is varying with time, and the calculation process might be complicated. So it's due to maybe some aging factors of the circuit breaker, for example. So it takes some times to switch on, switch off, for example. I mean, it's open circuit, to open the circuit. So that's why it's a lot of factors. That's why it could be quite complicated. So the cable can be sized based on the interrupting capability of the circuit breaker or fuse. Okay, so it's depend on what type of the fuse or circuit breaker that you use. Okay, for the fault clearing times, this is to calculate the fault clearing time only. So this is one of the time factor for the T just now. It is not the total time factor. Fault clearing time is only one of the components you need to consider, okay, for the T, in order to calculate for the T. So this is one of the calculation you need to consider. For medium, and I mean for medium voltage systems, for 4.16 kV breakers, I mean the fault clearing time we use is 5 to 8 cycles. So how to calculate the 5 to 8 cycle? So cycles means if you have a 50 hertz, 50 hertz. So 50 hertz, how many cycles? So 50 hertz, of course, it is 1 over 0.02 second, one cycle. So that means one cycle is 1 over 50. Okay, so if 5 cycles, means it's 5 times 1 over 50 second. Okay, so if 8 cycles is 8 times 1 over 50 seconds, 1 over 50. This is calculated in second. I mean, you can transform it into the seconds. Okay, so if that is the 50 hertz, if 60 hertz, that means if 5 cycle means 5 times 1 over 60. 1 over 60 seconds. There you can calculate for that. Okay, because one cycle for 50 hertz is 0.02 second. Okay, and then you just multiply with 5, 8, or etc. Okay, so for the current limiting fuse, if you are using fuse, so the time is much more shorter. So it is just half cycle only. Half cycle means is 0.5 times 1 over 50. So if we are using the 50 hertz. Okay, so for low voltage breaker with intermediate or short time delay, so we use 10 cycle. Okay, so for low voltage breakers with instantaneous trips, we use 1 to 2 cycle. This is for instantaneous trip. So it's much shorter as compared to the conventional types of these circuit breakers. Okay, example here, you consider a feeder is serving a large motor, so you feed from LV 415 volts or 400 volts switchgear having a circuit breaker with separate multifunction motor protection relay. So in this case, it is a Siemens, types of this one. And then we try to calculate what is the minimum fault withstand durations. Okay, the instantaneous setting for the cables. Okay, so the first one, we need to consider the relay sensing. So how much times the relay sense it needs, that means the pickup time, the pickup. So we consider 20 milliseconds in this case. This one is from the manufacturers. Okay, so it's 20 milliseconds. The tolerance delay times 10 seconds. The breaker operating times, that's why it's very subjective. It's depend on the condition of your circuit breaker, as well as the manufacturer's data. The breaker operating times is for 40 milliseconds. The breaker operating time, that means it's open. Opening time. So the relay overshoot, so if the current is too much, then it will have the overshoots. The overshoot until it's stabilized it took 20 milliseconds. So for the safety purpose, the margin, we add another 30 milliseconds. So the total is 120 milliseconds in this case. Okay, so therefore the cables XLPE, so that means we use XLPE as the insulator. we use the conductor aluminium, selected for the circuit breaker control model fits. So that's why we can calculate for the K. In this case, we can calculate for the K already. And the switchgear shall be suitable to withstand the maximum rated fault current 50 k ampere, the kilo ampere. So this is the fault current, this is the I. Remember just now I square T, I square. So this is the I, for at least 120 milliseconds. So this is the T. But this T is not yet finalized, not yet finalized, because we need to consider another criteria. However, an allowance of 40 milliseconds in the opening times of the circuit breaker is due to the aging. For example, the aging. So aging, that means it open slower, or it will open slower. Frequent number of operation increase in contact resistance. Then we need to add another 40 milliseconds to 120. So that means our T now is 120 plus 40, which is 160 milliseconds. Okay, 160 milliseconds now. Okay, and now we can calculate what is the minimum cross-sectional area, or we call it as a size. Size for the short circuit current withstand capacity. That means the criteria 1. Okay. So I short circuit is 50 kA just now, and the 50 kA times this is 0.16 is from here, 0.16. This is in seconds. So anyhow, you need to calculate in seconds. This is in seconds. You need to transform 160 millisecond to second, 0.16 here, square roots, and then divide by 94 K. K is 94. Where we can obtain the K? So it is aluminium XLPE. Then we go back to the previous one. Aluminium XLPE is the 94 here. Okay, so it's 94. Otherwise, you can calculate it using this one. 250, 90, and then you put in here. You put in here. Then you also can obtain the 94. Okay. And then from here we know that so the units, the final unit for A is in mm square, So this is our size, the cable size unit. Okay, so after all that, so you can calculate, it is 212.766 mm square. So this is the size, the cross-sectional area of our cables. From the criteria 1. It's not yet finalized because we need to analyze it further for criteria 2 and 3. So it might increase further, this one. So the next standard cable size is 240. So how to determine the next cable size? So we have 212. Of course, we need to choose a little bit higher than this one, the next cable size. Okay, the next cable size, we have the tables here. So we have tables here. So you look at the table. Here the current carrying capacity. Okay, so this is for multi-core and the armored cable. This is the armored cables for the copper. This is for copper. I just show you the example. You have another one is the aluminium. Okay, so the most important is the conductor size here. So from this is calculated in mm square. So from 1.5 minimum until 400. Okay. So just now we calculate 212. So 212 is about this one, between 185 to 240. So that's why the next size is for 212 is 240. So that's why we choose 240 in our next cable size, right? And I explained a little bit on this one. So this is how you read these tables. Is this you have a few 1, 2, and 3 columns. The column. So the column first column is the method C. Second column is method E, and the final one is the method D. So method C is the clip directly. That means you clip directly your power cables, power cables, and you have, of course, the single phase and a 3-phase. What this is 1, 3 core or 4 core. That means if you have RYB plus the neutral, that means you have a 4 core. 4 core. I mean you can use this column. If you are using the single phase 2 core only, then you can use this column, yeah, to find this is the current and the current capacity. For example, if you choose 240 ampere, then your methods on the installation is clip directly only. Okay, then you choose for 3 core or 4 core here, and then the maximum current carrying is 409 ampere only. Okay, that means the withstand current or ampacity of this cable is 409 only. Okay, so the second method is method E. Method E is in free air, in free air or on a perforated cable tray, like I showed you previously, perforated like this one, like this one. Okay, so this is on in air or in the tray. So if you are laid your cable or install a cable like this one, that means you are at the category of method E here. Okay, so method E, then it has a little bit change in the ampacity. Here it's 240, let's say just now 409. So if you laid your cable like just now, like this one, in the cable tray, so that means the ampacity is increased to 445. Okay, so finally, of course, it is underground. So this is for underground. If you lay your cable underground, then you can know the ampacity. So ampacity is much more smaller, only 280, due to the grounding condition. Okay, so this is the so-called the short circuit current withstand capacity criteria, which is criteria number 1. Okay, criteria number 1. So I will see you in the part 2 for the criteria 2 and 3, as well as the rest 2.6 and 2.7 of our chapter 2. Right, thank you very much. See you later.